Okay, so we're in section 5.2 now. We're going to talk about diagonalization. This is the last section in chapter 5 that we cover. So chapter 5 is very short for us. There's more to chapter 5 that is worth looking at. It's optional content for this course, but it's material that's better left for a second course in linear algebra. So let's get into this. Now, before we can talk about diagonalizing a matrix, we need to start with a more general topic called similarity. We say that two matrices, matrix A and B, are similar, or more specifically, we say that A is similar to matrix B if there exists an invertible matrix P such that B equals P inverse A P. Okay, I'm not sure what the in there is for, so we'll get rid of that. Now, the definition here might seem a little bit odd. It seems like a strange relationship to care about, that two matrices that can be related in this way. But it turns out, as we're going to see in a couple of minutes, that if matrix B is, or if matrix A is similar to matrix B, then these two matrices will share a lot of very interesting properties. Okay, and that's useful for reasons we're going to come across later. One thing also worth noting is that because P is invertible, I can solve this equation for A. If I were to multiply both sides of this equation on the right by P inverse, it would cancel this P. And both sides on the left by P to cancel the P inverse, I would get A by itself, giving me A equals PB P inverse. P is equal to the inverse of its inverse. So what this shows is that A is equal to the inverse of a matrix times B times that matrix, which also shows that B is similar to A. So in other words, if A is similar to B, then B is also similar to A. And for that reason, we can use the term, or we can just say A and B are similar, and there's no confusion about what we mean there. This symbol here, the tilde, I don't think is used in your book, but it is a common symbol for similarity. So if you see this appear, we read this as A is similar to B. So to start, I want to go through an example of showing that two matrices are similar. Here's a couple of 2x2 matrices, A and B. And one thing I do want to point out is that even though it's not stated here that A and B are square matrices, but this definition implies that they have to be. And here's why. If P is invertible, we know that only square matrices can even be invertible. So let's just say that P is an n by n matrix. It's square. Its inverse would also be n by n. And in order for this multiplication to be defined, A would have to be n by n. The product of three n by n matrices has to be an n by n matrix, so A and B are also n by n matrix. So that shows that not only are all four of these matrices square, but they also all four of them have the same dimensions. So if A and B are 2x2 matrices, then P and P inverse would also have to be 2x2. Now here I'm giving you this matrix P. It's 2, 4, 0, 2. And this is the matrix that I'm going to claim is going to show that A and B are similar. I have not shown where I got P from. And I'm not going to show that because we're going to come up with a method for finding the matrix P in a special case later on. For now, we're just going to use this matrix and its inverse, which we've computed here, to show that A and B are similar. What that boils down to is just taking the matrix A, multiplying it on the left by P inverse, and then on the right by P, which I've done here. It's just basic matrix multiplication, so there's no point in going through all the details. We do, in fact, get this matrix here, which is B. Okay? Now, that is all it takes to show that two matrices are similar. And again, I'm not telling you where I got these two matrices from, where I got P from, but you can see that it works. Okay? So we care about similarity, the relationship of similarity between two matrices, because of these things called similarity invariants. A similarity invariant is a property that two similar matrices will always share. So here we see, your book proves this first one, so I'm going to let you look in the book for that one. If two matrices are similar, then they're always going to have the same determinant. And we can verify that in our example up here. We showed that these two matrices were similar, and if you'll notice, both of their determinants are equal to 0. Okay, so we could check that. Invertibility. If two matrices are similar, then they're either both invertible or both not invertible. And again, that kind of follows from the case of the determinant. Both of these have determinant 0, therefore neither of them are invertible. Notice also, I could see some people getting a little confused by this. If two matrices are similar, by definition, the matrix P here has to be invertible. But as we see here, A and B don't have to be invertible. They can, but they don't have to be. Okay? We're not going to show this, but it is amongst our list of similarity invariants. Two similar matrices will always have the same rank, same nullity, same trace. We also see that here. Again, because these two matrices are not identical, but the trace, which is the sum of their main diagonal entries, is 1 in both cases. They have the same trace. Okay? They have the same characteristic polynomial. We're going to prove that on the next page. That would imply that they have the same eigenvalues and that their corresponding eigenspaces are going to be or are going to have the same dimension. All of these properties are always true of any pair of similar matrices. Okay, let's look at the characteristic polynomial example that I mentioned. Our goal here is to show that if two matrices are similar, then they have the same characteristic polynomial. I had a couple of typos here. That's a B and that's an A. So I'm going to say, suppose that A and B are similar. In other words, we have an invertible matrix P where we can write A as being equal to P inverse BP. Okay. Now let's suppose that we know the characteristic polynomial of B. I'm going to call it P lambda, P of lambda, but we know that to compute it, it's the determinant of lambda I minus B. This is where you get that characteristic polynomial from. With this, I want to see what the characteristic polynomial of A would look like. So we're going to attempt to compute that here. Okay, this is how we find its characteristic polynomial. However, A, as we assumed up here, is equal to P inverse BP. So I'm going to change the A into P inverse BP right here. Also, at the same time, I could be written as P inverse IP. And to verify that, notice this I is the identity matrix. So squeezing it in between these two matrices right here doesn't change anything. I times P is just P. That leaves me with P inverse P, which we know is equal to I. So what I'm doing is I'm making this look much more complicated, but for a critical reason. This next step, the only thing that changes is I took my lambda and brought it in here with the I. That's from homogeneity of scalar multiplication. We know we can do that. Okay. Now, if I look within this determinant here, I have two terms, each of which has a P inverse being multiplied on the left and a P being multiplied on the right. By the distributive property, I can pull each of those out and represent that this way. P inverse lambda I minus B in parentheses there times P here. Okay, next thing I want to do is use that really important theorem that we came up with in chapter 2, the multiplicativity, which is kind of a cumbersome word to say, of the determinant. I can break this into three determinants because there's a product in here. This would be the determinant of P inverse times the determinant of lambda I minus B times the determinant of P. Now also in chapter 2 we showed from that multiplicative property actually that the determinant of the inverse of a matrix is the reciprocal of the determinant of the original matrix. So the determinant of P inverse is 1 over the determinant of P. But notice if I wrote that this way, I have another determinant of P showing up over here. I'm multiplying two reciprocals together, which makes them equal 1. That leaves me with just this determinant right here, determinant of lambda I minus B, which, as we said up here, is the characteristic polynomial of B. So what this shows is that the characteristic polynomial of A is equal to the characteristic polynomial of B, which is what we showed in that table in the previous page. Okay, so the last thing I want to do for this video, and then we'll kind of get more into some examples in the next video. I want to show, or I want to talk about the term diagonalizable and what it means to diagonalize a matrix. That's the main topic for this section. So we say that A is diagonalizable if A is similar to a diagonal matrix. So in the relationship of similarity, if I say A is similar to B, to say that A is diagonalizable would be to show that B could be a diagonal matrix. So if that's the case, if A is diagonalizable, and if trying to establish that P inverse AP is a diagonal matrix, then we say that P diagonalizes A. We're going to go into a theorem here that's going to be really useful for this topic of diagonalization. But before we do, why might that be a good thing to know if a matrix is diagonalizable? Well, again, it goes back to these similarity invariants. If I know that A is diagonalizable, then I can find a diagonal matrix that it's similar to. Now, diagonal matrices are like our favorite matrices because they're the easiest type of matrices to work with. For example, if you're trying to find the eigenvalues of a diagonal matrix, we know that it's just the diagonal entries of that matrix. But if A is similar to a diagonal matrix, then we can find that diagonal matrix, read off its diagonal entries. Those will also be the eigenvalues of A. It makes that process simpler, finding those eigenvalues. And we get all of these other properties for free as well, which are really easy for to determine for diagonal matrices. So let's talk about a theorem, and this is what we're going to do to wrap this first video up. The theorem is going to be important in the method that we talk about for diagonalizing a matrix. So we're going to say let's let A be a square matrix. It's n by n specifically. If A is diagonal, let me say that differently. A is diagonalizable if and only if A has n linearly independent eigenvectors. It's an if and only if proof, so we have to prove both directions. So I'm going to start by using the assumption that A is diagonalizable. By definition, that means that we have a diagonal matrix D such that D is equal to P inverse AP. This is what it means to be diagonalizable. A is similar to a diagonal matrix. Now, another way of writing this same equation, if I were to multiply both sides of this by P to cancel this P inverse out, I could write it this way. PD equals AP. It's the same thing, okay? Now what I'm going to do is be a little bit more specific about what each of these matrices look like. Not all of them, P and D in particular. So I'm going to say let's let lambda I through lambda n be the diagonal entries of D. There would be n of them because like what we said before, if A is an n by n matrix, then so should all of these other ones, P and D. That would imply that D has a total of n diagonal matrices as well, one for each row. And I'm going to denote the columns of P by P1 through Pn, okay? And we're going to go back to a representation for multiplication that we talked about way back in chapter 1. AP, which is the matrix that shows up on the right side of this equation right here, can be written this way. If I represent P as a partitioned matrix and write its columns in here, we showed way back in chapter 1 that the product of A times this matrix looks like this. AP1, AP2, all the way through to the last column, APN. It looks like the distributive property, even though that's technically not what that is. Also, PD would be equal to this. We know that with diagonal matrices, if I multiply any matrix to a diagonal matrix where the diagonal is on the right side, then each entry on the main diagonal of that diagonal matrix is being multiplied to an entire column of this matrix here. So PD will look like this based on what we know about diagonal matrices. But we said that PD and AP are equal to each other. That means this matrix is equal to this matrix, which implies that their columns are equal to each other. Corresponding columns are equal to each other. So AP1 is equal to lambda 1p. AP2 is equal to lambda 2p. And this is what it means for something to be an eigenvalue of a matrix, right? So we know that This would imply that P1 is an eigenvector of A, and lambda 1 is the corresponding eigenvalue. P2 is an eigenvector of A, and its corresponding eigenvalue would be lambda 2, and so on and so forth. Therefore, all of those P1 through Pn vectors are eigenvectors of A. Finally, because P is invertible, because of our equivalence theorem, we know that all of those vectors are also linearly independent. That completes that first part of the proof. If A is diagonalizable, then it has a total of n linearly independent, or we can find n linearly independent eigenvectors for that matrix. Going the other direction looks very, very similar. In this case, we're supposing that A has n linearly independent eigenvectors, and again, we call them P1 through Pn. The idea here is to use these to construct the matrix P to establish that A is diagonalizable. We're also going to call the corresponding eigenvalues for these eigenvectors lambda 1 through lambda n, just like before. We'll use this to construct the matrix D. Okay, so again, because they're eigenvectors, that implies that we have these relationships, A P1 equals lambda 1P, and so on and so forth. We're going to construct the matrix P out of those n eigenvectors, and we're going to construct the matrix D out of those n eigenvalues, making these the diagonal entries of D. Okay, so if I were to do that, I could go through similar, I could do the same work that I did up here to show that AP is equal to PD. I'll let you look at that to see where the logic comes in. So the last thing to do is to show that A is diagonalizable, which means I have to write D of the form P inverse AP. Now you might be looking at this and say, well, yeah, just multiply both sides by P inverse on the left, and that wraps this up. But you have to actually know that P is invertible to be able to do that in the first place. That's not an assumption that we made. However, because we constructed P out of these n column vectors here, and because we assumed that these would be linearly independent, our equivalence theorem would say that this is an invertible matrix. If a square matrix has, if all of its columns are linearly independent as a set, then that matrix is always going to be invertible. So that allows us to do this last step here, which establishes that A is diagonalizable. Okay, in the next step, we're going to come up with a method for finding this matrix P using this proof here, but we're out of time for this first video.